I will not make out with you. You chose what you were about to do with this,
Hey, how come my fart moment got edited out, but that wasn't edited out? It's a big
He's quoting Billy Madison. So, all right, here we go.
AJ, that stinks. Ew.
All right, so we're starting. So, obviously, this is a very important section, given by the name of the section, Fundamental Theorem of Calculus. I will erase that. So, obviously, it was discovered by Newton. Newton's considered the father of calculus. Oh, congratulations. And Leibniz. And actually, you could use this theorem for things you do in physics. This actually can be even done sometimes in chemistry too, or even biology. Before we look at FTC, is how we'll abbreviate it, Fundamental Theorem of Calculus. That's kind of what we did yesterday, or yeah, actually that was yesterday. When we want to take the antiderivative, then we plug in. So it's a way of evaluating the, just put that way, please. Evaluating the definite integral. So the first thing we'll do is we'll start with the graph of y equals f of t. And we know that the area under the curve from a to b is that, right? That's the way we defined it. The definite integral gives you the area beneath the curve. So say we pick any x value in this range. So, I don't know, let's say right here. And shade the area of the curve from a to x. So it'll be like this. Check if I do it better than that. Okay. So in this case, the key idea is that now different choices for x results in different areas, right? Depending on where you place x. You know, if I put x, like say over here, like between a little bit to the left of b or maybe a little bit closer to a, you also get different areas. So basically the area is a function of x. Depending on what x is, the area obviously could change. So we can write the area like this. So little a is a constant. Times dt. There you go. So that's just something we just want to consider. Is that the area beneath the curve, depending on what you define for x, the area will be a function of x. Let's look at another one here. So if we look at integral functions, and again, these functions defined by integrals involving finding areas, right? We've talked about this, how we can find the area. So let's fill in the following chart. First of all, we're graphing y equals 4. Actually, I'm going to use red so it stands out. Yeah, go ahead. We're just trying to show the area is a function of x, that's all. Depending on what we choose for x. Okay.
Also you know how like when you derivative of the dx was derivative? If capital F is an antiderivative of little f, why do you take the also derivative of f over the denominator? Is like why do you take plus?
We take derivative of low f, you mean?
Like why do we just take the problem of
Wait, okay. I didn't quite understand the question, but okay, that works. So here's the deal. What if x is negative 4? So let's say I were to shade this. So we're looking at this situation, right? What if x is negative 4? So I'm integrating from negative 2 to negative 4, a 4 times dt. What would our area be here? What would you report? If x is negative 4, meaning I replace this here with negative 4, and I work this out, and looking at the shade area that I just did, what would that area be? No. It's negative 8. Why negative 8? You're right, it's 8, but because we're going from right to left. That's the reason why. So you have to look at where the boundaries are located. Because A is obviously greater than B in this case. So that's why it's negative 8. Now if I do negative 3, so if I were to readjust this, what was that? That's a negative 4 up here. Right here? That's negative 4. That's 4. Because that's your function. Now here, if I did that, I think now you guys know what to expect. What would that area be? It would be negative 4, right? And if I did negative 2, I would get 0. How about if I did negative 1? 4. Okay, so you guys are getting this. If I do 0, yeah, if I did that, now that's positive 8. One, be 12. And then 2, I would get 16. So you start noticing something here. Every increase in x by 1 causes an increase of the area by how much? By 4, right? The other thing, too, we notice is that when x is 0, the area is 8, right? So we can actually try to come up with a formula here in terms of x. Does anyone want to take a stab at what that formula would be? Well, let's think about it. The height's always what? Area is based on type. Well, that's 4, right? What is the base going to be in terms of x? Like, x is right here, right? I mean, x could really be anywhere. Heck, I could put x right here. So you want to take the difference of the x coordinates for the base, right? So your base will always equal x minus negative 2, right? Which becomes what? X plus 2. Yeah, I don't think it's very obvious just by looking at the table, but if you think about it, the height's always going to be 4. For the base, we'll always have negative 2 as a boundary, but x could be anywhere to the left or to the right of it. So the distance between x and negative 2 will get you the base. So that's what area is 4 times x plus 2. Or we could say it's 4x plus 8. If you want to distribute. By the way, before I move on to the next page, that was just the same thing, because you can always reverse it, right? Find area from negative 3 to negative 2, but then make sure you do negative, right? So. Oh, sure, go ahead. So this is important. And try to understand the fundamental theorem of calculus, because if you think about it, what we're trying to do is we're going to be subtracting the b and a values after we take the antiderivative. Because what is the antiderivative for? If you took the antiderivative out, that's going to be 4. What was that? No, if you took the if you took the antiderivative of 4t, sorry, I think I said 14. 4t, is that what you're saying? Sorry. And then if you were to plug in x, you have 4x, right? If you plug in -2, you'll get -8, and then we take the difference, you have 4x minus negative, which is 4x plus 8. So it's kind of what we're trying to work our way towards. There's another way we can look at it too. So here's -2. Here's x. The height's always 4. And the base, again, is always x minus -2, which is x plus 2. Again, all this right here is shaded. So we see the area is 4 times x plus 2. What was that? This is a 4. Right here? Where? I don't know. But x. Yeah, it's an x. I'm sorry. All right. So let's try another one. With a of x equal 1 to the x, or the integral of 1 to the x of t minus 1 times dt. Okay, how's t minus 1 going to look? What kind of function is that? Yeah, it's linear. And where does it cross the y-axis at? Good, and slope is 1. So if I kind of graph this a little carefully, she is. Okay. Now if you think about it, we're starting at 1. And let's say I go towards -1. So what if I were to find that area? What would that area be? Close. Oh wait, you're sorry. It is 2. Sorry, I thought you forgot to take half. Yeah, it is 2. Because you have 2 times 2, but you got to take half of that, so it's 2. Okay, what if change this up? That's not good. Because that's 2. If I change it up and do this, what would that area be? Half, right? And also we know that if you take a negative integral from 0 to 1, of f of t times dt, same thing as 1 to 0. So you can also look at that way as well. Because if I were to do, yeah, go from 0 to 1, and then take negative of that. 1, obviously we get what? That's not going to work. Let's redraw it. Cool. All right. You have 1, we get 0. How about 2? What do you guys think? What's the area now? If I'm integrating from 1 to 2, I want to find the area between the the curve in the x-axis from 1 to 2. No, it'd be positive half. Because it's above the x-axis, and you're going from left to right. That's because we're going from right to left. That's the reason why. That's why I was trying to say over here. Okay, how about if I do 3? Try to find that area. That'll be 2. How about if I do 4? From 1 to 4. What do I have? Well, we'll have 6. 4.5, because the base is going to be 3 and height's going to be 3. Right? So you have 4.5. So if we think about it, what is a of x? Well, it's not so obvious. Define an expression for a of x in terms of x. Because the height always changes, and the base always changes. The rectangle is easy. The height was always the same. When you saw the base was just the difference of the x values, right? Or between x and -2. So let's think of it another way. So here's 1, 0. And here's x. Now, I already know that my base, how can I write my base in terms of x? What would be the length of my base in terms of x? X minus 1, good. Remember area of a triangle? 1/2 dh. So 1/2 x minus 1. Now let's look at the height. What would your coordinates be here in terms of x for this point right here? If we're calling this x, so what would the x coordinate be? It's not a number. No. Think about it. These have the same x coordinate, right? So that's just x. Now how about the y coordinate though? Well, in terms of x. Remember our equation is this, right? Y equals t minus 1. So if you replace t with x, what do you get? X minus 1, right? So x, x minus 1 is a general way you can always state that coordinate. So height's going to be what then, in terms of x? X minus 1. So essentially, when you integrate 1 to x, t minus 1 times dt, we're expecting this. Because that's the area beneath the curve. So you have 1/2 x squared minus 2x plus 1, distribute, yeah, I think it's right. Let me clean it up here. Okay. So let's go on to the next page. So this is what we had, right? This expression we got, that the integral was 1/2 x squared minus x plus half. Now what if I took the derivative of both sides with respect to x? Remember, you're taking the derivative and doing antiderivatives. So it's almost like they're knocking each other out here. If we think about it, if you take the derivative of the right side, what would you get with respect to x? What if I take derivative of this? What do you get? You guys can do this. Come on, it's really simple. X minus 1, right? Because if you have 1/2 x squared, and we move the 2 down, x to 1, those cancel. And then, of course, derivative negative x negative 1, derivative plus half is just 0. So what this means, f of t is t minus 1. F of x is what? If you replace t with x, you get x minus 1. So that's the fundamental theorem of part 1. The fundamental theorem of calculus part 1 states this right here, that if you take the derivative with respect to x of the antiderivative from 1 to the x, you're basically just going to get the same thing. So it kind of shows how these are inverses of each other. You take a derivative, take an antiderivative, and if you're going from 1 to x, you're basically going to get the same function, but this time it'll just be in terms of x. So that's one of the theorems, or that's one of the parts of FTC. And it's basically in 2 parts. So if f is continuous on from a to b, then the function, the antiderivative, capital F, remember represents the antiderivative, will equal that. And for every point for x in the interval from a to b, if you took the derivative, remember that's the derivative of your antiderivative, maybe actually make that more neat. Think about it, this right here is capital F of x. We'll get you back to little f of x. Because you're doing the derivative of the antiderivative, right? Which are almost like 2 operations that knock each other out. And I think we could probably finish this off really quick here. So here's the thing. Every continuous function is always a derivative of some other function. And vice versa, every continuous function also has an antiderivative. The antiderivative will also be continuous on that interval. And this is the key thing. Notice that I've been using the word inverse a lot, right? They're inverse operations of each other. And we're going to start getting to a lot more integrals later on. So obviously for this one here, it's almost like these knock each other out. So what would the derivative of the antiderivative from 0 to x is sine t times dt be? Just sine x, just sine x, that's all. What about if I change it up? Instead of 0, what happens to negative pi over 4? Does it really matter? Doesn't matter. Notice I did 0, we were doing 1 before. It doesn't matter. Because you're taking the derivative with respect to x, but your upper limit's x, you have sine t times dt, so these two just don't matter. I mean, for anything you define for a, it just doesn't matter. A just needs to be a constant. Okay, maybe I could squeeze in one more. So in this case here, what would it equal? 5 over 3 plus x squared. If you took the derivative of this with respect to x. If you took the derivative with respect to x of the antiderivative from negative 2 to x of 5 over 3 plus c squared times dt, you just get the same thing. And what do you guys think about the last one? Example 3. What was that? Good. Why negative? Exactly. The negative secant x says x and 7 are switched. Because you need x up top for it to be positive. Because now you're going the other direction. Now you're going from right to left instead of from left to right. So it's negative secant x for that one. Okay, so we'll do more of this tomorrow. All right. So we're all set. You have homework. It's going to be light, though. Very light.